All right, let's dive into one of the most exciting frontiers in AI right now, graph neural networks. We're about to unlock this hidden story that's woven into the data all around us, a story that, honestly, most of our tools completely miss. Okay, let's get into it. So, I want to start with a question for you. I mean, we are just swimming in data, right? But what if we're constantly ignoring one of its most powerful dimensions? What are we missing? Well, this is how we usually see data, in these neat, tidy rows and columns. This is a classic data set from the Titanic. Every row is a person, and every column is a fact about them, their age, class, whether they survived. It's organized, it's definitely useful, but it's also kind of flat. And that flatness, well, that's the problem. It means we're missing what might be the most important part of the whole story, the relationships. Who is traveling with who? Who are family members? Who are friends? All of those connections are practically invisible in a spreadsheet. Just look at the contrast here. On the left, you've got our familiar table. But on the right, that's the same data, but visualized as a network of family relationships. All of a sudden, you see this whole web of connections. And you realize that for a lot of people on the Titanic, survival wasn't just about their age or what class they were in, but about who they were connected to. That right there, that's the hidden story. So, here's our game plan. We've seen the problem, those missing relationships. Now we're going to look at how to fix it by thinking in graphs. Then we'll meet the network smart AI that's built for the job, see it in action in the real world, and finally take a peek at what's next for this amazing technology. Okay, first up, thinking in graphs. And I want to be clear, this isn't just about a new type of chart. This is a fundamental shift in how we actually see and structure information itself. And it all comes down to two really simple ideas. A graph is just a collection of nodes and edges. Nodes are the things, the entities, people, molecules, web pages. And the edges, those are simply the relationships that connect them. Friendships, chemical bonds, hyperlinks, you name it. So you see the circles here? Those are the nodes. Sometimes they're called vertices. And the lines connecting them, those are the edges. That's really it. It's this beautifully simple way to make relationships a first-class citizen in our data. Okay, so now we have this whole new way to see data. But how do we make sense of it? I mean, how do we actually give these graphs a brain? Well, that's where a very special kind of AI comes into play. Meet the Graph Neural Network, or GNN for short. This is a special type of AI that is literally built from the ground up to learn from graph data. It doesn't just look at the features of each individual node in isolation. It learns from the entire network structure, how everything is connected to everything else. So how do they really work? Well, the simplest way to think about it is that GNNs let the nodes talk to each other. In each step, every single node gathers up information from its direct neighbors. It kind of summarizes all that info and uses it to update its own state, its own understanding. And then it passes that new understanding along in the next round. It creates this amazing cascading flow of information across the entire network. And this is the key difference under the hood. On top, you've got a conventional neural network, which just takes in flat data. But down below, the GNN has these special graph updating layers. This is the engine room where all that communication happens. In these layers, each node does exactly what we just talked about. It gathers info, it aggregates it, and it updates itself. And this happens over and over again, allowing information to literally spread across the entire network, making the AI network aware before it even starts its other learning tasks. Okay, so this all sounds great in theory, but where is it actually making a difference? Let's look at GNNs in action, because the applications are already, frankly, incredibly impressive. Take drug discovery, for instance. We can represent a molecule as a graph, right? Each atom is a node, and the chemical bonds between them are the edges. A GNN can then look at that structure, learn from it, and actually predict the molecule's properties. This is dramatically speeding up the search for new medicines. Or how about physics? Researchers are using GNNs to build AIs that can get a sort of intuitive understanding of the physical world. By treating objects as nodes and the forces between them as edges, the GNN can learn to predict how things will move and interact, a lot like we do. And this isn't just happening in a lab. GNNs are running at a massive scale right now. Pinterest built a GNN called PinSage to power its recommendation engine. They created this gigantic graph where pins and boards are different kinds of nodes. The GNN then learns the complex relationships between all of them to suggest what you might want to look at next. And get this, the results were staggering. By understanding this whole network of content and users, Pinsage was able to improve user engagement by 30%. That is a huge leap, and it's all because it understood the relationships that the traditional methods were missing.
So you see the pattern here, right? That's the crucial point, how versatile this framework is. For molecules, the nodes are atoms. For physics, they're objects. For Pinterest, they're pins and boards. The pattern is always the same. You identify the things, you identify the relationships, and boom, you can build a graph to start solving the problem.
So let's bring this all together. What's the one big idea you should walk away with from all of this? It's really this. GNNs are so powerful because they finally give AI the ability to understand the most important and often hidden feature in our data, the relationships. You know, this quote from one of our sources just says it perfectly. In graphs, the links and relationships in our data are first-class citizens. They're not some afterthought buried deep in a table anymore. They are the central focus of the entire analysis. And that shift in perspective, that changes everything. And that leaves us with a final, pretty exciting question. Now that we have the tools to see and to understand these hidden networks all around us, in biology, in society, and technology, what truly groundbreaking problems are we going to solve next?